Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 31st, 2025, just 3 days ago. It finds that iteratively deploying large language models and fine-tuning them on curated data from their predecessors can more than double their performance on complex planning tasks. The paper is titled, Iterative Deployment Improves Planning Skills in Large Language Models. And as we'll see later, this emergent self-improvement behaves exactly like a reinforcement learning process, even without explicit rewards. Alright, Figure 2 summarizes the main results across 3 planning domains: Blocks World, Rovers, and Sokoban. The bar chart tracks the number of solved tasks, comparing the base model, shown in hatched lines, against subsequent generations up to Generation 5 in yellow. Across the board, performance skyrockets. For instance, in the Rovers domain, the success count jumps from just 41 in the base model to over 200 by Generation 5. Similarly, Blocks World and Sokoban see their success rates roughly triple, confirming that this iterative loop consistently drives major improvements. So while the previous chart showed the outcome, Figure 1 illustrates the training loop that drives it. It starts at the top left, where input prompts are fed into the current model, labeled Generation N. The model generates plans, which then pass to an external validator on the right to filter out failures. Crucially, as the center shows, the system combines these new valid plans with successful traces from all prior generations. This cumulative dataset then feeds into the supervised fine-tuning step at the bottom, which produces Generation N+1. Okay, having established the training loop, Figure 3 tracks the resulting performance trajectory across 5 generations. On the left, Panel A displays the average number of solved tasks. Notice the sharp initial rise, particularly for the Rovers domain in orange, which quadruples before leveling off. However, the right-hand chart, labeled Unanimous at 3, reveals a deeper trend. This metric measures reliability by tracking tasks solved in 3 consecutive runs. Unlike the average, this consistency score climbs steadily even in later generations, meaning the models are not just getting lucky, they are becoming fundamentally more robust. Well, to put those performance gains in perspective, Table 1 details the complexity of the tasks used in the evaluation. It lists the specific parameter ranges that define difficulty for each domain. For Blocks World, the tasks involve rearranging anywhere from 2 to 10 blocks, which creates exponentially larger state spaces. Similarly, the Rovers domain scales from 1 up to 5 independent agents, while Sokoban puzzles require manipulating between 1 and 7 boxes. This variation ensures the models are tested on a diverse spectrum of difficulty. So, Table 1 defined the difficulty, but Figure 4 reveals whether the models actually tackle harder problems or just memorize simple ones. These heat maps show the distribution of plan lengths for Blocks World on the left and Sokoban on the right. The vertical axis represents plan length, while the horizontal axis tracks the generations. In the Blocks World plot, the base model on the far left shows activity only in the bottom rows, meaning it generates short plans. But as we scan right to Generation 5, the bright yellow intensity shifts upwards into the 24 to 31 step range. This proves the model is genuinely learning to solve longer, deeper planning horizons. Alright, while the previous heat maps confirm deeper planning, Table 2 asks a critical question. Is this improvement driven by data quantity or curation quality? It compares the average number of solved Blocks World tasks under 2 regimes. The middle column, using the standard curated approach, shows the score jumping from 52 to 154 by Generation 5. In contrast, the rightmost column shows that without curation, simply feeding back all valid traces, performance stagnates around 79. This demonstrates that selectively filtering for high-quality plans is essential for the rapid capability gains we observed. Wrapping up, 2 takeaways stand out. First, simply iteratively deploying and curating data acts as a powerful reinforcement learning loop, driving emergent reasoning skills without explicit rewards. Second, this hidden reward mechanism poses a safety risk, as models might evolve unpredictable behaviors based on opaque user feedback. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.